Hey all, so here we have a little thing that we're going to need to demonstrate that's going to give us something really useful in like probably literally the next video. So our goal here is to consider the matrix A transpose A for a given matrix A. And our claim is going to be that that matrix A transpose A is invertible if and only if A has linearly independent columns. You're going to note here that I spelled if wrong. That's intentional. So the if with two F's means if and only if. So if you haven't seen that symbol before, I haven't used that in class before, essentially that means these two things are equivalent, right? So A transpose A being invertible is exactly the same, right? It implies and is implied by A having linearly independent columns. So our first thing here is that we're actually going to make a just a completely different claim that doesn't feel like it has anything to do with anything. Oh, but before I do that, one thing. First thing I should just note right off the bat is it even reasonable to talk about invertibility here? So my first thing I'm going to note is that if I take A transpose A, that no matter what size A is, this thing is square. And we can kind of think about that as like, all right, if A is, say, M by N, then A transpose is N by M. The M's say we can do this multiplication, and the N's say that we're going to end up with a square matrix. So hopefully that's straightforward, relatively simple, cool, good to go. Next thing. So our next thing is this kind of alternate claim, right? So I'm going to make a different claim here, and then I'm going to show you that it's basically the same thing. So my kind of different claim is going to be about null spaces. So my claim is going to be that the null space of A transpose A, right, this matrix that I'm talking about, is exactly the same as the null space of the matrix A. So the way I'm going to do this is I'm going to show that I'm first going to show that the null space of A is smaller than the null space of A transpose A. Right? That's going to be our first thing. And then our second thing is going to be to show that it's actually also bigger. So if I show that a number is smaller, right? Like if I show that X is smaller than 2 and also that X is bigger than 2, that would tell me that X has to be 2 because it can't be both smaller than and bigger than without actually just being the thing. The same thought applies with sets. So I'm going to show that the null space of A is contained in the null space of A transpose A, and then I'm going to show vice versa. So for our first way, this one's pretty straightforward. We're just going to say, let's let X be in the null space of A. Then we're going to consider, so we're going to consider A transpose A done to X. Well, but A transpose A done to X is just A transpose done to the zero vector because X is in the null space. A transpose times the zero vector is going to be the zero vector. I'm good on this one, right? So that's one direction, check. Second direction is going to be a little bit more complicated. So our second direction is going to be that I'm trying to show that the null space of A transpose A is smaller than the null space of A, right? So this is me showing the opposite direction. So for this, I'm going to say, let's let a vector x be in the null space of A transpose A. And then we're going to try to demonstrate that that thing actually has to be in the null space of A. So the way I'm going to do that is I'm going to write down what it means to be in the null space of A transpose A, right? So that means that A transpose A done to X gives me the zero vector. Probably fix my transpose so it looks half decent. Okay, good on that. All right, next thing I'm going to do is I'm going to take this and I'm going to dot product this whole thing with X. So I'm going to do X dot producted with A transpose AX. This is going to be X dot producted with the zero vector. That's going to give me 0. Now, this doesn't feel like it got me anything, and it kind of didn't. So what I'm going to do is I'm going to say, all right, I'm going to rewrite that with a transpose. So that's going to be X transpose A transpose AX. right? This is just me using that trick I've used a few times over the last couple days that I can write a dot product, right? So that's kind of just to recall over here. So the thing I'm using is that x dotted with y is equal to x transpose times y. All right, so now I'm going to look at this and I'm going to say, oh, wait, I've got these two transpose matrices next to each other, right? So I'm going to rewrite that as AX transpose times AX. And I'm going to know that this is zero. Oops, sorry, I was trying to fix my handwriting and made everything worse. Okay, so this then is actually just AX dot producted with itself. Oh, whoops, I lost something here. Do you guys see what I lost? I did something a little dumb. So a second ago, I wrote down x dotted with x dotted with zero is the zero vector. That's not correct. It's the zero scalar. So this is the zero scalar. So this is the zero scalar. Sorry about that. That's my bad. Just writing too fast. All right. So I've got ax dotted with ax. So that tells me that that's really ax's magnitude squared is equal to the zero vector. Then the zero scalar again, I'm getting myself screwed up. So that's going to mean that AX itself has to be zero, and that's going to be the zero vector. So because the dot product of AX with itself is zero, that means that the magnitude of the vector AX squared is zero, and the only vector with a magnitude of zero is the zero vector. So that tells me that X is in the null space of A. Okay, now here's the deal. So we're going to go through a couple of little implications. So I'm going to kind of summarize over here. Well, okay, I'm going to write an implication chain. It's kind of like a summary. So here's what I know. I know that the null space of the matrix A transpose A is the same as the null space of the matrix A. What that means is that, so that means that if, sorry, let me rephrase. That means that A having linearly independent columns is the same thing as the null space being the zero vector, right? So A has linearly independent columns is equivalent, right, to the null space of A being just the zero vector. And what that means, because I know that these two null spaces are equal, is that A has linearly independent columns is the same thing as the null space of A transpose A only being the zero vector. And that then means that A has linearly independent columns is the same thing as A transpose A being invertible. Now, there's one thing here that I feel like is a little bit subtle. Why is it that I automatically know that A transpose A is invertible and I didn't know that the matrix A is invertible? It's a relatively subtle point. So pause the video here, take a second and think about that. All right, thanks for coming back. I'm sure you paused the video and thought about that. The reason is that that matrix A isn't necessarily square, right? I just know it has linearly independent columns. I don't know that matrix is square, but I do know that A transpose A is square, and so it's a candidate for invertibility automatically. So what I have here is at the end of my little chain, I have A having linearly independent columns is the same thing as A transpose A being invertible. That is my claim that I've got up top. So I'm going to call this a day. Thanks for watching, guys. I'll catch you in the next video.